Good morning, students. We have come to the last unit, Unit 5. This is about applications of partial differential equations. And of course, we have seen earlier about the differentiation and integration. And this is about partial differential equation. The difference between ordinary differentiation and partial differentiation lies with the letter, the symbol. Ordinary differentiation, it is referred as D. But this is curly. So this will be curly D. So sometimes we will denote as del, or sometimes even dou. We used to say it's as dou. Mainly we are going to deal with two applications. One is about the wave equation, another one is about the heat flow equation. So we are going to deal only these two. An ordinary differentiation, we are going to differentiate with only a single variable. Whereas in partial differentiation, it depends on function which depends on many variables. So we have a function which depends on many variables, and we are going to differentiate with respect to only one variable. Other variables we are going to keep it as constant. So this is the idea. And in single direction, this variable will change. Say for example, if we have 2 or 3 variables, and which is a function, the function contains 3 or 4 variables, and we are going to differentiate with respect to only one variable, and we are going to keep other variables as constant. So this is the idea about partial differential equation, and mainly it is used in physics and engineering subjects. Especially in physics, it is used in quantum mechanics, electromagnetics, fluid dynamics, and all other areas. People use these partial differential equations. So we are going to discuss mainly on one-dimensional wave equation and heat flow equation under partial differential equations. So we have one idea, we are going to use one idea, but we are going to use other idea. So here we are going to have the idea about the methods of separation of variables. Here this is ordinary method. So in this unit we are going to cover the topics of partial differential equation for transverse vibrations in elastic strings. What we call this as one-dimensional wave equation. And another main application is one-dimensional heat flow equation. Solutions to these partial differential equations by the method of separation of variables. And we are going to discuss with some problems based on boundary conditions and initial conditions. Partial differential equations, it is a differential equation involves partial derivatives. So which is denoted as curly D. A partial derivatives represent the rate of change of a function, a physical quantity, with respect to more than one independent variable. So more than 1 or 2 variables. It can be either 3 or 4, ... Independent variables in partial derivatives can be spatial variables represented by x, y, z in Cartesian coordinate system, or r, theta, z in cylindrical coordinate systems, or rho, phi, z in some other coordinate systems. Rho, theta, phi in spherical polar coordinates. The temporal variable represented by the time t. Examples of partial derivatives will be partial differential equations can be categorized as boundary value problems, or initial value problems, or initial boundary value problems. The boundary value problems are those problems that the complete solution of the partial differential equation is possible with specific boundary conditions. So we are going to have initial and final boundary conditions, and we are going to solve. The initial value problems are these partial differential equations for which the completed solution of the equation is possible only with the specific information at one instant. So this is the definition of a partial differential equation, which goes like this: a partial differential equation involving partial derivatives of dependent variables, one or more, with more than one independent variables, is called a partial differential equation. Okay. So as I said earlier, the curly D is denoted for this partial differential equation. So this is not a particular D, straight D, it is curly D. Okay. It means it's a partial differential equation, and mu is a function which is having more than one variable, more than one independent variable. For example, here mu is a function of x and t. So that's why it's written as d to the power 4 mu divided by dx to the power 4 plus d to the power 4 mu divided by d to the power 4. See here, there are two variables, x and t. mu is a function of x and t. Okay, so this is what the partial differentiation means. So here too we have z is function of x and y. See, you have x is a variable, y is a variable. They are all independent variables. So z depends on x and y. Z is a function which depends on x and y. So if there are two variables, we can say that this is a partial differentiation. Okay. For example, when you take this, xi is a function of say x and y, f is x and y, and p is d psi by dx, it can be, or q is d psi by dy, or s is d squared psi by dx dy, or t equals d squared psi by dy squared. Any equation containing partial differential coefficient is called as partial differential equation. It is used mainly, as I said earlier, fluid mechanics, fluid dynamics, quantum mechanics, heat transfers, so are the areas of applications of partial differential equation. There are two categories in partial differential equation. One is linear and another one is non-linear. So linear, as far as we are concerned, this is a linear one. See, we have a linear equation. For example, when you take y equal to mx plus c, it is a linear equation. So it's a straight line. If it is curved one, what we call this as non-linear equation. For example, y equal to x squared or ax squared, then this is curved one. Curved one is a non-linear equation. So this is general definition for linear and non-linear. As far as this equation is concerned, see, look at this equation, and this equation is heat flow equation, and this heat flow equation is nothing but a linear equation. So this is a linear equation, and this is non-linear equation, and you have the power here. Whenever you find some power, it is a non-linear equation. Simple idea. Whenever you find some products, it's a non-linear equation. X and y together, we call this as non-linear equation. So this is linear equation. There's a power here. So there's a power here. So it's a non-linear equation. So any equation involving partial derivatives of an unknown function of two or more independent variables is nothing but partial differential equation. So classifications, as I said earlier, linear and non-linear. This is a second order. See here, we are going to differentiate two times. So second order linear equation, and this is, we are going to differentiate three times here. See here, three times. So this is your third order linear equation, and there's a power here. See here, there's a power here, as I said earlier. So this is non-linear equation, and there's a product here. So this is a non-linear equation. So simple idea. Classification based on characteristics will be your first order partial differential equation. Almost all first order partial differential equations have real characteristics and therefore behave much like hyperbolic equations. So hyperbolic equations of second order. Second order PDE. So second order partial differential equation in two dependent variables x and y may be expressed in the general form exactly as shown in the slide. Now, lot of applications. Out of all the 5 applications, we are going to learn mainly 2 applications. One is heat equations and wave equations, which belong to our syllabus. So that's why. So there are different topics which are used: Laplace equation, heat equation, wave equation, fluid dynamics, and in quantum mechanics. And this is the equations of different applications. See, for example, we take wave equation. So we have only wave equation is represented in terms of this. So this is a linear equation. This is also a linear equation. See, we are going to differentiate 2 times here. We are differentiate 2 times here. We are going to differentiate only once. So this is the only heat equation. This is only wave equation. Okay. And of course, we know Laplace equation. This is 2 variables are there. So this is 2D Laplace equation. And which is equal to 0 Laplace equation. Which is not equal to 0. This is Poisson equation. So here it is equal to 0, right hand side, homogeneous equation, and this is equal not equal to 0. So this is Poisson equation. Only 2 variables are there. So it is 2D. So this is 2D wave equation. 2D wave equation. Okay. See here both are the same. And the last one is 3 variables are there. So 3D Laplace equation. And of course, if it is not equal to 0, we can say that this is 3D Poisson equation. Is it okay? Poisson equation. See here, u is a function of u, x, y, z. 3 variables. Here it is 2 variables. See, here it is 2 variables. Here also we have 3, x, y, t. Here we have x, y, 2 variables. So there's a mistake here, x, y, t. So x, y, t. So here it is 2 variables. and here again two variables, that also will have two variables. Differential equations. A differential equation is an equation involving an unknown function and certain of its derivatives. So we are going to have the derivative, first order derivative, second order derivative, and goes on. An ordinary differential equation is an equation involving an unknown function of one variable and certain of its derivatives. A partial differential equation is an equation involving an unknown function of two or more variables and certain of its partial derivatives. So these are the examples of different equations. So these are the initial boundary conditions. Only then we can solve partial differential equations. So these are the initial conditions. First derivative equal to y of t, which is where t lies between 0 and L. And the solution of this will be y prime represents a dy by dt. Okay, dy by dt, which is equal to y of t. So the solution will be y of t c1 e power t. And here 2 times we are going to differentiate. See, 2 times. The solution will be this one. Okay, boundary conditions. See, these are the boundary conditions. Y of 0 equal to 1 is the boundary condition. Okay. Similarly, we can have this is the boundary conditions, which we'll see later. So this is one boundary condition. This is another boundary condition. Okay. So we have 1D equation, and these are the possible solutions. You have to remember the possible solutions like this. So we have possible solutions for this differential equation. Okay, and we'll be using the boundary conditions. So these are the boundary conditions which we'll use. We are going to solve. We'll be solving later. So let us solve. So this is the equation, wave equation, and solutions will be exactly like this. And we are going to use all the boundary conditions. You have to learn by heart. 4 boundary conditions are there, and we are going to solve one problem. Okay, let us solve the problem. We'll see. So first problem: a string is stretched and fastened at 2 points. See, at 2 points we are going to stretch and leave it. So we have 2 points. One is x equal to 0, another one is x equal to L. So we have 0 to L string. I am going to stretch and I am going to elongate. Okay. Motion is started by displacing the string into the form y equal to k times Lx minus x squared. So this will have some oscillation. Suppose if one string is tightened on the other side, I am going to pull it, I am going to leave it. The string will have this oscillation. This oscillation will have the motion in the form y equals k times Lx minus x squared, from which it is released from the time t equal to 0. We are going to find out the displacement. So we are going to find the displacement, which is nothing but y of t or y of x. We'll see. So 1D wave equation is given by this. This is one solution. So this is what I told you. You have to learn by heart 3 solutions. See here, this is one solution. So equation A is the solution of this differential equation, partial differential equation. What are the conditions? Conditions are given. Here y depends on x and t, correct? There are 2 variables. X is a variable, t is another variable. So y depends on both the variables, correct? So y is a function of x and t. Y is a function of x and t. What's given here? X is 0. This is one boundary condition. X equal to 0 here. See here. Y is a function of x comma t. X is 0 here. The answer is 0. So this is one condition, one boundary condition. Second one is y, it is on the other side, L comma t equal to 0. Is it okay? Your x equal to L, because your string is L, 0 to L. So x equal to L. And here d by dt you are going to differentiate, and y of x comma t equal to 0 here. This is another boundary condition which is equal to 0. And the last boundary condition is at t equal to 0, we have k times Lx minus x squared. So we have to write this one. So these are all 4 boundary conditions, because there are 2 variables. We are going to keep the first x equal to 0, then here is x equal to L, and here t equal to 0 and t equal to 0, and we are going to write the same. We are going to write the given in the problem. Okay, so let us solve. So we are going to apply the condition 1. So this is equation 1. So equation A, we have 4 conditions are there. So we are going to apply first condition, which is x equal to 0. This is equation A. So we have y of 0 comma t which is equal to 0. So we'll have to write 0 here. Okay. Now we'll have to write x equal to 0 in equation A. X equal to 0, so that will cos 0. Cos 0 is 1. So A plus what of sin px? Sin 0? 0. So we have now A multiplied by c cos pat plus d sin pat. See here. This is equal to 0. According to the boundary conditions, this is equal to 0. You have to learn by heart all the 4 boundary conditions. So this is equal to 0. So either A equal to 0 or this term equal to 0. So it implies that A equal to 0. So we have first result A equal to 0. So if A equal to 0, you substitute here. You substitute in equation A. So if A equal to 0, this term will not appear. So we have only this term alone. So we have this term alone. Is it okay? Simple one. Now we are going to use the second condition in equation B. So this is equation B. Second condition is x equal to L. Y of x comma L, correct? X comma t. So y of L comma t which is equal to 0. So y of L comma t, wherever instead of x you are going to substitute L. So in equation B, instead of x you are going to substitute L. So b sin pl cos pat plus d sin pat which is equal to 0. So either this equal to 0 or this term equal to 0. Okay, we are going to assume that p should not be equal to 0. P only possibility is sin pl equal to 0. If sin pl equal to 0, the condition goes sin n pi. For all n pi it is 0. We have already learnt earlier. Sin n pi equal to 0. We have learnt earlier. So sin pl equal to 0 implies that sin n pi. So sin pl equal to sin n pi. So pl equal to n pi. So p equal to n pi by l. So instead of p you can substitute n pi by l. Wherever you find p you can substitute n pi by l. So equation B becomes B y of x comma t which is equal to b sin px here px. Instead of p you are going to substitute n pi by l. And c cos instead of p you are going to substitute n pi by l. So n pi at by l. Instead of p you are going to substitute pi n pi by l. So this becomes like this. So this is equation C. We have applied two conditions now. Now we have to apply third condition. Okay. Third condition is we have to differentiate with respect to t. Correct? Can you remember? So we will have to differentiate with respect to t. So differentiation will give you this. So this is equation C. We are going to differentiate with respect to t. So we are going to keep this as constant. We are going to differentiate this with respect to t. We are going to differentiate this with respect to t. Because these two terms only contain t. See t. This is constant because it doesn't contain t. It contains only x. See here. Now you are going to differentiate this. When you are going to differentiate, this will become minus c sin n pi at by l n pi a by t. Similarly here plus d times n pi a by l cos n pi at by l. Is it okay? See. Now we are going to apply the third boundary condition which is equal to t equal to 0. Okay, so we will have to apply here at t equal to 0. When you are going to apply t equal to 0, this term it will appear like this, and here t equal to 0. What of this term? T equal to 0, sin 0 0, so 0. Okay, cos 0 is 1. So we have d times n pi a by l, so which is equal to 0. So 0 equal to b sin n pi x by l d pi a by l. And we have already seen earlier that b cannot be equal to 0. We have seen, see, we have kept b is not equal to 0. So b cannot be equal to 0. Only possibility is d can be equal to 0. So now substituting d equal to 0 in equation 3. So this is equation 3. So we have now y of x comma t which is equal to b sin n pi x by l c times cos n pi at by l, because this is 0. So now to find the general solution, we will have to use Fourier series of, can you remember this one? Bn. Fourier series sine term. Okay, we have DC term, we have cosine term in Fourier series, and we have sine term. Correct? So we are going to use only sine term. So that goes like this: y of x comma t which is equal to summation over n equals 1 to infinity bn sin n pi x by L cos n pi at by L. So now at t equal to 0, we have to substitute the fourth condition at t equal to 0, y of x comma t, y of x comma 0, which is equal to k times Lx minus x squared. It is given in the problem. See here, it is given in the problem as I said earlier. So we have to use in the last condition, we have to use this one. So this becomes t at t equal to 0, this one will go off, cos 0 is 1. So we have only bn sin n pi x by L. So this is for f of x. Now we have to solve for bn and substitute here, that's the answer. We have to solve for bn, and of course we know bn is given by, according to Fourier series, 2 by L, 0 to L. This is, can you remember what is this one in Fourier series? This is half range Fourier series, 0 to L. 2 divided by L, 0 to L, f of x sin n pi x by L dx, where f of x is given as k times Lx minus x squared. So k times Lx minus x squared. So now we have to integrate. And of course we know integration goes with Bernoulli's formula. Bernoulli's formula is this one. So here u is nothing but your Lx minus x squared and v is nothing but sin n pi x by L. So we have to differentiate and we have to integrate. That's Bernoulli's theorem. And after that we are going to substitute in this way. We are going to substitute in this way. Next term will be 0. So only we will have only 3 terms. So we have only 3 terms. This will be the first term. With the minus sign we have the second term. With the plus sign we have the third term. So we have only 3 terms. So this is first term, second term, third term. Okay, 0 to L. And of course we know the limit will be limit 0 to L. So we have written 0 to L. So this is your first term. See here, first term. This will be your second term with a minus sign. One minus is there, already you have minus sign. So that's why it is plus. And the last one already we have one minus sign. See here we have one minus sign. So we have minus sign. Now let us substitute the upper limit first. When you are going to substitute the upper limit, instead of x you are going to substitute. Okay. So this becomes L squared and this becomes L squared. So 0. Is it okay? You are going to substitute the upper limit. This is your, instead of x you are going to substitute L. So this becomes L squared. You are going to substitute for x, you are going to substitute L. This is L squared. L squared minus L squared, 0. Okay, so this term will go off. And what about this term? This term. You just substitute, instead of x you just substitute L. This L and this L will go off, correct? Sin n pi is 0. So this term also becomes 0. Is it okay? Is it okay? See here, instead of x you are going to substitute L. And L and this L will get cancelled. We have sin n pi. Sin n pi is 0. So this term will go off. What is the last term? N pi L by L. L will get cancelled. Correct? So we have now minus 2 cos n pi. Cos n pi is minus 1 to the power n, which we have already learnt. Cos n pi is nothing but minus 1 to the power n. Cos 0 is 0. Cos 0 is? Cos 0 is 1. Cos 0 is 1. Cos pi is? Cos pi is minus 1. Very good. Cos pi is minus 1. Cos 2 pi is? Cos 2 pi is again 1. Cos 3 pi is minus 1. Cos 4 pi is 1. See, alternatively. We have 1, 2, 3, 4 alternatively. So that's why we written minus 1 to the power n. Okay. When n equal to 0, what is the answer? When n equal to 0, what is the answer? 1. When n equal to 1, cos n pi, cos pi, when n equal to 1, cos pi is minus 1. Minus 1 to the power 1 is minus 1. Is it okay? Is it okay? So similarly we can write, instead of cos n pi you can write minus 1 to the power n divided by we have n cube pi cube by L cube. Similarly you can substitute the lower limit. When I am going to substitute the lower limit, this will become 0, of course. Correct? When I am going to substitute the lower limit, this will become 0. This, what of this? Sin 0? 0. Very good. So this term will go off. What is the last term? Cos 0 is 1. We have minus sign. Already 1 minus sign will be there for applying lower limit. So minus minus plus. So cos 0 is 1. That will give us 2 divided by n cube pi cube by L cube. This is the last term. So this will be this term and of course 2k by L. So now we can simplify. We can simplify. So this becomes 2k by L. We have 2k by L, and we can add these two, pulling 2 out. So we have 2 common, see here, 2 as common, we can pull it out, and we have the similar terms here. So this becomes Bn equal to 2 2s are 4, 4k. We have L cube and L, that will give us L squared. So L squared divided by n cube pi cube, 1 minus 1 to the power n. So Bn is given by this if n is odd. N is even. Suppose if n is even, n equal to 2, n is even. So this becomes minus 1 squared. What is the answer? Plus 1. So 1 minus 1, answer is 0. So if it is even, answer is 0. If it is odd, the answer is this one. Is it okay? Now we have found out now Bn. So here y of x comma t equals, we have to substitute in Fourier series, sine Fourier series, we have n summation over n equals 1 to infinity. So this is the expression for your Bn. Bn is nothing but 8k L squared by n cube pi cube sin n pi x by L cos n pi at by n. So this is the most general solution for 1D wave function of a string having length L which is stretched. Okay, so this is the answer. We have found out now y is a function of x comma t. So there are 2 variables. We have found out the solution. So this is the answer. Any doubt?